The next topic in the third and last bit of this tutorial is about Python containers and HPC. So we're going to see some examples of MPI and GPU-enabled containers, and then a final one on Intel-optimized Python. The first one is MPI. I'll try to make the story a bit shorter compared to what is in this paragraph. What we want here is to squeeze bare metal performances out of a supercomputer, right? What makes us, one of the essential ingredients in a supercomputer is the high-speed interconnect that makes communication between nodes fast, right? We want to retain that. One thing is to say, okay, well, I can live without Cascade Lake optimizations in my code, but I can't live without interconnecting an MPI-enabled code. So we need to get that right. That's crucial when we are speaking of MPI-enabled applications, both outside or inside containers. And so we need to talk a bit about this. There are two models that people suggest around, and you can see some discussion in a Singularity documentation page with the link here. One is the hybrid model and one is the bind model. So in the hybrid model, what you do is that you configure and build everything you need for your cluster in the container. So say that you know that your container has a given MPI installation and a given interconnect configuration, and you try and replicate that configuration, which takes into account the interconnect library installation and everything in the container. This makes the container more complex, but crucially, it breaks portability completely. I mean, that container will only run decently in that cluster if you did the right things in the Docker file, and that's it. I personally prefer the bind model. That's the one we are going with at Pawsey. In the bind model, you rely on the host MPI and interconnect libraries at runtime. That way, you decouple the process of building the application with the process of making sure it runs with maximum performance in relation to the interconnect configuration in your supercomputer cluster, which kind of makes sense. I mean, one thing is you can perfectly build a working application which is MPI enabled without knowing the interconnect configuration. This is two different things. That's because 99% of Linux installations make use of dynamic library linking. It means that when you launch an application, if that application needs a third-party library, say the MPI library, it doesn't ship it in the binary file itself. It will look for the library it needs in the file system at runtime. So if you can basically even swap the library you're using, you're relying on your application at runtime. And that's what we exploit with the bind model. That way we can have a generic installation of the MPI application in the container, and then just ensure that the Singularity configuration in the supercomputer cluster is right and enables using the interconnect as it should. So there are a few ingredients to get there. Of course, the supercomputer will have an MPI installation with interconnect libraries properly configured under the hood, and that's it. I mean, that's provided by the HPC center. But then you still need an MPI installation in the container to build and compile the MPI-enabled application, right? And there is a little thing is that you need to ensure that the application is linked dynamically to the MPI libraries, and the application knows which library needs to look for. Well, the dynamic link bit is basically the default in all Linux OSs but Craze. But in the container, we are using Ubuntu or Debian or so on, so that's fine. Still, in our Docker file for the mpich based image, we add a little bit just to ensure. Sorry, I picked the wrong one. Let me see. Sure, I can show you I can show this to you in the Docker file we just used. When we build the MPI, so downloading, configure, make install, this ldconfig command is there because honestly, I might be saying that in a poor way because I'm not an expert, but with a broad jargon, what this is doing is making sure that the binary knows that it is looking for in this case, rewind. We are telling the operating system that there are some new libraries, the MPI libraries compiled in a given path, and they're available for dynamic linking, so that the linker in the container knows that they're there, and then we'll use them at build time later on for MPI for Pi in this instance. But then it will also link the MPI for Pi libraries in such a way that when you actually use them at production, they will be able to eventually swap and use other libraries at runtime. So it's just a little step to ensure that in some installations, everything will still work without the LD config. But I don't have an example, but there are cases where this could break. So it's just safe to ensure that the configuration of the dynamic link is right with this command. Have you got any comment, Pascal, on this?
I was just going to say that I normally think that you really should have that. I don't know that that is, you can guarantee that it's going to be the case if you don't have that there in any OS. Maybe they do it by default, but I would imagine that just to make sure, you should have that there. For anything that you're going to do that you feel like you're going to swap it. So if you're running stuff where you want to make sure that you're installing the library, but you want to make sure that it's swappable for whatever's on the host, then I would suggest that you actually make sure that you run LD config. I could be wrong, but I think that's the case. You can't guarantee that it's going to be there, so always do it.
Perfect. If you know a computer scientist, just go poke him and ask for more details and maybe more appropriate jargon. This is this is what we can try and explain to you in this specific regard. But this makes things working. So you are achieving an MPI installation in the container that is swappable at runtime, which is what we need, so that at runtime we can use the host optimized and performing MPI and interconnect libraries in a supercomputer. Last ingredient, second last ingredient. There are different MPI flavors and brands out there. That most of them are open source, but still there are many. MPitch, OpenMPI, MBAppitch, and Intel MPI, and IBM MPI, and others. It turns out that not all of them are compatible with all of the other ones. And this is because of application binary interface compatibility. Actually, it turns out, the story is quite simple. It turns out that OpenMPI is only compatible with OpenMPI. All of the other flavors are compatible with each other. So basically, if you know that your supercomputer has any MPI library but OpenMPI, all you can do is just to always use MPitch in your container, and you know that that will be compatible with any MPI library in the host, with the exception of OpenMPI. If you really need to run with OpenMPI in the host, in the supercomputer, then you need to build an image which has OpenMPI installed. At Pawsey, right now, all of the systems have at least one MPI compatible library. So it's Cray MPitch on Magnus and Galaxy. It's Intel MPI in the other ones. So that's why in our examples here we're using MPitch. This is also what we are supporting for MPI-enabled code as regards the last point of these ingredients and requirements. So in this bind model, what you are doing in practice to be able to use the host, the supercomputer, MPI, and interconnect libraries at runtime is to bind mount the locations of where those libraries sit in the host. It could be Magnus, Zeus, or whatsoever. And we're doing that with the singularity bind path environment variable. I'm going to show this an example in a minute in one of our clusters. And then we also need to use singularity and LD library path. Because it's not enough just to make the library files available. You also need to tell the shell where to look for libraries when you execute any application. And there is a Linux variable for that. It's called LD library path. And so unless the libraries are a generic system location, USR, lib, or similar, which is not the case for MPI libraries on Pawsey. So they are in specific paths. So you need to provide those paths. And because you are providing them in a container, in a singularity container, you want to prepend singularity env to the definition to make sure that singularity defines these variables as it should. In this way, you are effectively providing and exposing the host MPI and interconnect libraries to the container at runtime, so that when you run your MPI application, it will use those and not the container ones. And we're gonna now play a bit with this, so because I want to convince you about this aspect, which is quite crucial if you're using MPI-enabled code. So let me start with opening an SSH session on Zeus. So at Pawsey, we are providing this bind mounting configuration with these two singularity variables out of the box for you. So it's basically in the singularity module. So if you do module show singularity on any of our systems, you see there is a singularity env LD library path, which actually adds the path for the Intel MPI, for an Intel MPI location. And also in the singularity bind path, oh, and there's also user lib64. This is important. So Intel MPI path has the MPI libraries, user lib64 has got the interconnect libraries. Then we need to bind, this is just a variable definition. It's not mounting any files. With singularity bind path, other than bind mounting the important file systems or your data set, so Astro, Group, Scratch, Pawsey, we are also mounting a full bunch of files that are actually the interconnect libraries. We can't just bind mount user lib64 in block because it would break the container. User lib64 contains a full bunch of system libraries. You can't just mount them in the container. They would shadow the container once and break the container. So we need, that was a bit, that was tedious, but required. We had to cherry pick the list of interconnect libraries from our installations and ensure they're bind mounted here. So that when you do module load singularity, you get them. Okay. And now we're going to apply with those. So just in the interest of time, I've already converted our MPI for Pi image in singularity format. It's sitting here in this directory. It's n1 latest.cif. And so let's play with it a bit. We can just open an interactive shell. Let's locate MPI for Pi here. I'm going to use the find command, which is a Linux utility to find file names. Let's look for MPI for Pi. And I just did what I should not have done. So first of all, let's go and let's clean the environment. That won't be enough. It's just a bit, hold with me. I just don't want to have all of that output because it's just a bit messy. So I know that MPI for Pi is somewhere under USR. Okay, this is just a bit cleaner to manage. So let's go in this directory. This is in the container, right? This is where the Docker file installed MPI for Pi. We here have some files. Crucially, we have the MPI for Pi compile library. So there is a Linux command LDD, which can be quite useful in your debugging installations, especially if you need to play with dynamic linking of libraries and binaries. If you do LDD followed by a binary path or a library path, it will tell you all of the libraries that that object links to right now and at runtime. And here we go. Funny fact, this MPI for Pi library needs libMPI, and it's finding it under /Pawsey. So this kind of shows you the benefit of setting those singularity bind path and singularity and LD library path variable. Now let's unset the library path and repeat the command. And now libMPI is found in the container instead. So you see that the difference is really made by setting LD library path and mounting the right path from the container. This is just a little trick that it might be useful for you when you develop the container. Now I want to give you the taste of the performance with a quick example that ships with these workshop materials. Let me retrieve let me get an interactive Zerma location for this purpose. And task node 1. I hope there's something available. Yeah, possible. yeah. Thanks, Pascal. Queue, and I only need 10 minutes. Go. Here we go. Thanks. Okay, now let's try and use MPI for Pi. So there is here an hello MPI for Pi script that just prints information on the nodes that are being used by the run. So we can go singularity exec -e, and there should be M1 latest container, and let's go Python 3 hello, and let's use this run. That way we're going to use the two processes in the distinct nodes that I asked for. Here we go, two processes. But now for some performance. So in this, there is also an OSU bandwidth Pi script that is taken from this benchmark suite developed in the Ohio State University. It just does a bandwidth test with MPI for Pi. Should be two processes, right? That's funny. That's the beauty of the live sessions. I tried this in the previous days. It was fine.
Does it actually mean nodes?
You want the nodes to demonstrate the performance bit. It's funny because yeah, I tested it yesterday the last time. Right now, I don't see, I just give one more go. If not, I will just show you the outputs in the tutorial page. Okay. Well, good enough. So let me see if there's anything I've in tasks to node, right? Okay, interesting. So this is what I was running, right? And this is what you get, what I should have got as an output. And by the way, I got this exact output like yesterday from a test. Basically, it's testing some different package sizes from 1 byte to 1 megabyte. And here you get the bandwidth, and you see that it's around 8 gigs per second with 1 megabyte size. Now let's forcibly unset the LD library path when we execute the container. So I'm doing that here with bash -c. And first I'm unsetting the path and then running the benchmark again. And you see that the bandwidth drops to 100 megabytes. So again, this really demonstrates the difference between configuring the interconnect right or not. And by the way, if you run the same test, native bare metal without containers, you get the exact same results here. I have also some plots further down that so these are some much more extensive tests we've done with MPI in containers to show that native and container MPI performance with the right configuration are basically the same. Yeah, so there is also an H5Pi example that I'm skipping just in the interest of time. It's here in the documentation. And I'm still running a bit late, so if I may ask 10 more minutes of your time overall. I hope this is fine with you, because I want to show you the CUDA example and just a couple of words on Intel Python. Okay, so similar to the requirements I discussed with MPI, we have some requirements for GPU-enabled containers, which are hopefully kind of simpler. So of course, if you are installing or running CUDA-enabled or ROCm for ND enabled applications in the container, you will need to provide some essential libraries in the containers to build and eventually run that. The only bit that, if you think about that, the only bit that is specific to the site cluster is the accelerator driver. So that's the only bit you really need to get and bind mount from the host when you run the container. And Singularity provides a transparent interface to that. So you just need to add the --NV flag to Singularity exec, and Singularity will look for the NVIDIA drivers and mount them in the container. Same thing for AMD. There is a --ROCm flag, which is experimental right now. So that enables us, for instance, to go with CUDA-enabled numba, right? So numba is a package that allows you to optimize and accelerate your Python code with a kind of nice interface. It provides you both high-level and low-level APIs for CUDA and ROCm development, so it's quite nice. I'm going to show here an example how you would build a numba container for your GPU, your Python GPU workloads. So here it is a similar process to what I did with MPI. So I need Python, I need CUDA. I know there are base images for both. So I had a look at the NVIDIA CUDA image. It's about, I think overall it's 60 lines. It's broken down in 3 different images that are used, chained one on the other one as subsequent base images, but overall it's just 60 lines. So I just copy pasted those lines on top of a Python 3 base image. And this is what's happening in this Docker file. It's a lot of wget, apt-get, there's really not much happening, some environment setting and so on. Once that's done, there is the numba bit, which is actually quite similar to what we did with AstroPy. So we did the dry run, figured out the requirements, chunked them in a requirements file, and then pip install. And that's it. And that's how I got a numba Python container, which has CUDA capability. And so let's see if now I'm luckier with the CUDA container compared to the MPI container. So let me SSH into Topaz for this example. And we have an idle node. Yeah, that's a good starting point. Not too bad. So, okay. So let me get an interactive allocation on GPU QDev. And now let me go to the example directory, which should be this one. Yes.
Do you want to quickly show Marco the bind paths in Singularity here, which would show the CUDA stuff?
So yeah, thanks for the comment, Pascal. So there is no additional line for that. Okay. And that's because, and I'm going to show this to you actually.
You can do it that way, but I think it's tricky. So NNV should do it all for you.
Exactly. So NNV does it for you. The one bit that is not done yet is just the interplay of MPI and CUDA in case you have multi-node or multi-GPU code. I'm working on that. So right now there is no pre-configured support for that, but here we're just going for a very simple example of a little number script that just adds a couple of vectors together. So it's a vector X, then I create a vector that is which is 2x, and I sum them together, I should get 3x, right? So let's go with Singularity, srun Singularity exec -c. Let's see if I can find this CU1 should be the CUDA enabled container. And let's go Python and the add CUDA numba. And this will give an error actually. Why? CUDA driver library not found. And that's why on purpose, I didn't put the --nv flag here. So that's why you need that, because otherwise the NVIDIA drivers from the host are not bind mounted in the container. If you add --nv, Singularity does for you the task of looking for the CUDA drivers in the host. It works nice because CUDA drivers are normally just installed in the system directories, USR, lib, whatever. So that's it. You add the --nv, the Docker file at the CUDA and numba, and here is our 3x vector as an output. So we just ran these CUDA enabled containers just with this extra flag and with the CUDA in the Docker, in the container image. And so I hope this can be a useful starting point for you if you have any CUDA enabled Python workflows. As I said, for numba, you really need the full SDK, so the 3 GB version, because it's using some libraries there at runtime. So unless you have that, it won't work. If you only use CUDA code that is not numba, not Python based, you might be good with a smaller installation of CUDA. That's why they provide these 3 levels of Docker files. And the very last comment, and then I'm closing about 5 minutes, is about the Intel Python. So turns out that Intel for a few years now has been supporting an optimized Python installation, which includes MKL accelerated NumPy and SciPy, DAL accelerated scikit-learn, and more. So the framework is maintained as a Conda channel by Intel. So but there is also a ready-to-use container image, which is based on the mini Conda installation and just grabs some Intel packages from the Intel channel of Conda. So now suppose in this example, we're just, as AstroPy depends on NumPy, why not having an Intel optimized AstroPy installation in the container? And so what we're doing is just using the Intel Python core image as a starting point now. So this will ship with a couple of gigabytes or so worth of packages, including NumPy optimized by Intel. I'm just adding the Conda prefix as a best practice with Conda installation, as I showed in the previous session. And then and then what I did here under the hood, again, the usual requirement story. So do I run on top of the base image Intel Python here to get the full specification of requirements with AstroPy, and then really the same story that you saw with the Conda example earlier on. I'm just redoing it with Intel Python as the starting point. And that's it. So Intel provides some performance figures. So you may get some good speed up with linear algebra, FFT, some machine learning based on scikit-learn and other cases. I didn't have the time to rerun them myself. We were working on that. We got some confirmation that you might get some 10, 20, 30% speed up when using Intel optimized Python. It grows your image quite a lot. You need to use Conda, you have no other choice. I mean, you might want to play around with it if you like. And there is also an Intel iBench benchmark suite to actually test some of the optimized packages you're on. And then very last but not least, this might be useful tomorrow when we have a look at your pipelines. We've recently added support for a number of HPC Python based images designed by Pawsey. There are the images, there are the Docker files. So they provide a bunch of typical scientific computing Python packages: NumPy, SciPy, Matplotlib, whatever, scikit-learn. As I know that we have a good number of radio astronomers in the community of Pawsey users, there is also AstroPy already there. So it's there. You can have a look. There are currently a number of flavors. There are non-Intel and Intel optimized Docker files. There is serial H5Py, parallel H5Py, CUDA enabled, numba, non-CUDA enabled numba. So there is as much as 6 HPC Python Docker files currently supported by Pawsey, and hopefully they can be useful for your purposes. I wanted to mention this. With that, I'm just open to a couple of more questions in case you guys have any, or comments from Pascal or Alexis.
So I guess it's something I would mention, that at least the experience suggests that scikit, Intel optimized scikit-learn and NumPy and the FFT stuff is very useful, because there is quite a speed up. So if you're thinking of your workflows and there's a lot of that, then you may want to consider trying to construct an image from the Intel one, but it's big. But of course, you can also try doing, I mean, if you really want to get into it, you could obviously try doing it yourself and rebuild all these Python packages from scratch. But that, and maybe that's something that MWA could consider if they really want to try to do something. But normally, just to mention that they could be very useful for your workflows if you're considering it to kind of use the Intel optimized Python. If there's a lot of Python, then you're doing a lot of that calculations within using NumPy or scikit-learn.
Thanks, Pascal. So if there are no further questions, just spit some water. So if no further questions, I think we can close it here today. I'm sorry we went a bit longer with these prepared materials, but I hope that this can be useful and a good starting point for our work on your pipelines tomorrow. So tomorrow will be almost fully devoted to working on your examples. And actually, we will be happy to take any questions for you. We know that today there's been a lot of content that I went through. So reflect back on it today. And if you have any questions, we can start from a Q&A session tomorrow. Thanks, everyone, for attending today.
Thanks very much.
Thanks. Thanks, Marco. It was really good.
Yeah, thank you very much, Marco.
Hi, everyone. So welcome back to this online workshop series on containers for Python and radio astronomy. In this short session, I'm just going to go back to an issue that we experienced in the main session around running MPI-enabled Python containers. So you might remember that in the last part of the main session, we discussed the required setup to run MPI-enabled containers by reaching almost near bare metal performance, which requires properly configuring the MPI and interconnect libraries so that they are exposed in the container at runtime. But then, after the discussion, I was trying to show you a small performance example by using a script, a Python script that is based on the OSU micro benchmarks. So, and that's where we were then in the main session. So here I'm on Zeus. Let me enter this directory, which is just a Git clone of the workshop materials from the Pawsey repo. And let's go in the MPI4Py example from the third session. So here is the OSU bandwidth test. And so let me open as the interactive session with 2 tasks over 2 nodes on the debug queue just for 10 minutes. Now let me load the Singularity module. Now let's give it a go. So here we have this M1 latest container, which is a container that we discussed in the main session. It contains a Python installation and an MPI for Py installation based on npitch, which is present in the container. Then at runtime, dynamic linking will occur against the host Intel MPI libraries on Zeus, thanks to an appropriate configuration of the Singularity module. But let's recap what happened in the main session. So we tried to execute Singularity using srun, so to make use of the two cores across two nodes on Zeus. So using the M1 container and then running this OSU bandwidth test. Yeah, and it's now working. It wasn't working the other day, right? So why wasn't it working? Well, because the other day, I was showing you that a good practice to run Python containers on a host is to isolate the shell environment by using -c. So that basically cuts out any variable that is defined in the host shell. It doesn't bring it in the container. In that way, we can make sure we have no weird behaviors. And that's because we often have Python-related libraries on a machine, because Python is nowadays quite ubiquitous language and tool. So in this case, by chance, by ditching the environment isolation, the script still works, but in other cases, it might either not work or even yield undesired behavior. So the good practice is always to ensure that there are no spurious Python variables from the host. But then let's focus on this. So with the main best practice I showed you on the main session, we have a failure. And it took me a bit to understand what was going on, and that's because I'm praising this best practice. But then when I was designing the exercises, I was keeping on forgetting to use -c, and then I got the working behavior by accident. But then let's reflect on what's going on. So if we have a look at the environment in this shell, well, we've got lots of stuff, but crucially, we have a number of Slurm-related variables and Pmi-related, of Slurm-related variables. We can do the same from the container. So let's try this from the container. Let's use srun, which will make use of the resource manager of Slurm, so that the required resources, two cores across two nodes in this case, are actually bound to the runtime of the command. So let's go for Singularity exec -env, and then we have all of these Slurm variables, and some of these might be important, and actually also some Pmi variables. So Pmi is a piece of middleware that is important for handling resource allocation with the scheduler. And then, of course, if we isolate the environment of the container with -c, we lose all of these variables, right? And so we might be tempted to pass these variables in, but some of those are just dynamic. So I have a look at these Pmi variables. Some of these are just very specific to the actual command that is being executed, to the Slurm step that is being executed. So in this case, actually, so when we need to run NP applications from a container, we can't really isolate the shell environment, because we're going to lose these variables that are defined at runtime and that we need when we're running on with multiple processes or multiple cores and nodes. So we need basically to ensure that the host environment that now needs to be brought in the container is clean from variables that might interfere with the Python execution in the container. And basically, this boils down to unset these Python variables that are present. And so we can kind of automate this with a nice one-liner. So from the full environment of the host, we can grab all of the variables that, whose name starts with Python. And of course, in this way, we get the variable and its value. Then we can use cat with equal as a delimiter to just grab the name. Then let's turn this into a space separated list. And then let's unset these variables. And now they're gone, all right? So this is the workaround practice for running MPI-enabled Python containers. You need to unset the Python variables in the host first, and you can do this with this nice one-liner. And then now you can run whatever MPI for Pi script and or any other Python script, and be sure that there is no interference from the host environment. So for instance, we can now run our OSU bandwidth test. We don't need -c anymore. Actually, as you know, it will make S-run to fail, but now we don't need it anymore because we have unset the Python variables from the host. And here we go, our bandwidth test with a peak around 9 gigs per second for a 1 megabyte size packet. And now let's try and convince ourselves that this is really an improvement compared to the bottom line of the performance. So what we can do is the following. So prior to running the Python script, we unset the LD library path in the container runtime, which is the variable containing information about where the MPI and interconnect libraries sit. And now you already notice that the time to run the test is much higher. So this kind of gives you a hint, right? So if the time is higher, it's likely that the bandwidth is going to be much lower, so the performance won't be any more close to bare metal, which is what we don't want. Oh, taking some time. Here we go. Now we are peaking at only 100 megabytes per second. So once more, if we do not unset the LD library path, and we have no reason to do that, that's pre-configured in the Singularity module file for you, so that you get the right performance from the interconnect. So if we just run the test in the simplest way possible, here we go, we get the right performance that benefit from the high-speed interconnect in the cluster. Remember, just the key ingredient here is to unset the Python variables, and that's what was missing in the main session. And for your convenience, in the web pages of this workshop, I have added a note in the introductory session, number 1. So here there are some caveats, and we're talking about clean shell environment, and I was discussing the good practice of using -c. But here we go, I've added a warning for MPI applications, and I have reported the one-liner that allows you to unset the Python variables. I hope this can be useful for you. Thank you.